As we move into different portions of the solving quadratics, we're going to learn how to do the quadratic formula with. But prior to that, what I want to do is I want to examine some skills that will be useful as we go into that, and that will be simplifying radicals. Because in many ways, there's a giant radical in when I'm the quadratic formula has a giant radical in it, and I want to make sure that we're comfortable with simplifying it before we continue. So simplifying radicals, we want to remember that the radical expression is, we can simplify it using our multiplication and division properties, and that the multiplication and division properties of the square root or the radical are extensions of our exponents, because we did learn back in the exponents that the radical is really just a fractional exponent. We're not going to go so much into that fraction, but understanding that the same rules apply. So some of the things that we understand, that when I have the square root of AB, that is the same thing as the square root of A times the square root of B. Or if I have the square root of A divided by B, that would be the same thing as the square root of A over the square root of B. So I can rewrite these using those properties to help simplify. And as we go forth, we move, we're going to be using a lot of these interchangeably, but I just want to begin with that. Okay, so as we continue here, we're going to talk about removing perfect square factors. And what we need to do is remember our perfect squares. Our perfect squares are going to be, I call them the very important products, right? Perfect squares would be 1 squared, or 1 times 1 is 1. You have 2 squared, which is 4, and 3 squared, which is 9, and so forth until, at this point in time in your education, you should really know 15 squared, which is 225. But again, filling in some of those blanks, 4 squared is 16, 5 squared is 25, and then 6 squared is 36, 7 squared is 49. And why those are important is because when we're finding the square root, we are trying to find those perfect square factors out there so we can simplify them. So we're trying to we're going to work our radicals, our square roots, down to prime numbers that we can't do in our head. So when I look at the square root of 160, I know when I simplify that becomes, I can rewrite that as the square root of 16 times 10. 16 times 10, 160. And then I can separate those if I want, that I have the square root of 16 times the square root of 10. And now I can simplify this one. I know what the square root of 16 is. It's 4. But I do not know what the square root of 10 is, so we're just going to leave that in its radical, and I end up with 4 times the square root of 10. This is an equivalent expression of this. And that's what I'm trying to do, make it as simple as possible. I have a irrational number here that I can't myself find out what the square root is without a calculator. So as we go on, the next example is 72, and I'm looking for the largest perfect square that will go into 72, and it turns out to be, that would be 36. So 72 is the same thing as 36 times 2, so I can find the square root of 36 times the square root of 2. And again, I can solve for the square root of 36, and that's 6. I can't do the square root of 2, so I end up with just 6 times the square root of 2. So I've simplified these expressions. And moving forward into this next example, I have 125, which, you just start thinking about what's the largest number that will divide into that. And if I look at my perfect squares, I'm betting I can throw 25 in there, but this number and this number will not divide evenly into 125. So looking at this can be rewritten as the square root of 25 times 5, which we know is the square root of 25 times the square root of 5. And I can go ahead and simplify this one. I know that the square root of 25 is 5. I do not know the square root of the other 5, so I just bring it down. And there we go. We have the equivalent expression of 5 square root of 5 is equivalent to that, and it's simplified. There's no more operations that I can do there. So that's what we're doing when we're simplifying our radicals. So now we have variables involved. And I guess to remember the properties of variables, when we are exponents of variables, we need to remember that when we are multiplying like bases, we add the exponents. So let's see here. What is the simplified form of this expression? I have 54n to the 7th. Well, I have broken this up into some perfect squares. The 9 times 6 is going to give me 54. And then I have n to the 6 times n. Because this is actually a perfect square. And as an example, I know that if I have n to the third times n to the third, our exponent rules, we would have n 3 plus 3, because we are multiplying like bases, and then that would become n to the sixth. So therefore, I know that the square root of n to the 6 is n to the third. So we're just using those properties. So when I come here, and I know that I can find the square root of 9 is going to be 3, and then the square root of n to the 6th is going to be n to the third, and then I can't find the square root of 6 and n by itself, so I'm just going to leave them in the radical and bring them down, and I have 3n cubed times the radical, or the square root of 6n. So let's see as we move on to this next example. I have something going on here. I have some stuff on the outside of the radical. Remember, it's just multiplication. And I am going to break this up into its largest perfect squares. And I can rewrite this as I have negative m times the square root of, when I look at 80 by itself, 80 is going to be the factors of, 80 is going to be 16 times 5. And then m to the 9th, I'm looking for that even number because I'm going to find that perfect square. That's going to be m to the 8th times m to the 1st. Now, to show you, I think we can identify here that the square root of 16 is going to be 4. Okay, so I'm going to have negative m times 4 because I just found the square root of 16. Then I'm going to have the square root of 5, and the square root of m to the 8th is going to be m to the 4th. And then I can't find the square root of m to the 1st, so that just remains under the radical. And now I have some stuff that remains in the radical. Okay, m and 5 will remain in the radical because I could not find a perfect square for those items. But the other things I've moved outside the radical, I still have negative m, I have 4, and I have m to the 4th. So when I rewrite that, that's going to be negative 4m to the 5th. And I guess I could have put that a little bit closer. Negative 4m to the 5th. Negative 4m to the 5th times the square root of 5m. And it's m to the 5th because you got to remember this m over there is to the first power. So that is a simplified expression for that. And looking at the radical, again, there's no perfect squares left inside the radical. Okay. The square root of 243 x to the 5th. Now, I can tell you, if I look, I believe that 243 can be rewritten as the square root of 81 times 3. That would be 243 times x to the 4th times x. Because I can find some perfect squares here. Perfect square, 81, perfect square, x to the 4th. So the square root of 81 is going to be 9. I can bring that out of the radical, and the square root of x to the 4th is going to be x squared. And I'm going to have some stuff left in the radical. So I've gone and I've simplified those two, leaving behind 3x. And of course, just clean that up some. And that is my simplified expression for that right there. All right, so let's see, what do we have left? Now we're going to multiply two radicals together, which again is just extending what we've just done as we separated some of the perfect squares using that multiplication property. Now we're just going to combine them using that multiplication property. So looking at this example, I have 7 times the square root of 5x times 3 times the square root of 20x to the 5th. Well, I have 3 times 7 on the outside, and then I just reordered my radicals here. Then I simplified, so 3 times 7 is 21, and then of course I have this going on, which is going to be 100x to the 6th. And now when I do that, I have 21 times the square root of 100 times the square root of x to the 6th, which is going to give me 21 times 10. Square root of 100 is 10. The square root of x to the 6th is x to the 3rd. And then I simplify this, so I have 210 x to the 3rd is going to be a simplified expression. So as we move on, and you're going to develop, you may have your own shortcuts that you see. I'm just sort of breaking it down step by step. So here when I go to find this, rewrite this, and I have 3 times the square root of 6 times 18, which is going to be 3 times the square root of, well, gosh, that's 8, 4, 108. 3 times the square root of 108, and that is going to be 3 times the square root of 36 times 3, because 36 will divide evenly into 108 3 times. And now I know that I can find the square root of 36, but I can't find the square root of 3, so I'm just going to leave that in the radical. And so I'm going to have 3 times 6 times the square root of 3, which is going to be 18 square root of 3. There we go, and I just kept simplifying using what we were doing before. And let's see here, going on to our next example. Well, let's see here. If I want to, I can see a perfect square as I look. I have the square root of 2a times the square root of 9a cubed. Well, I know that this is going to be a perfect square, so I could go ahead and do that as I'm simplifying. But so if I do that and I bring that out, I'm going to have the square root of 9 is 3 times the square root of 2a times a to the 3rd, which is 3 times 2a to the 4th. And I'm hoping now you know that the square root of a to the 4th is going to be a to the 2nd. So I would have 3a to the 2nd square root of 2. And that is my simplified form of this right here. I could have done it. I could have just said, okay, well, that's the same thing as the square root of 18 a to the 4th, and I know that 18 is going to be 9 times 2, a to the 4th, which is going to be then 3 square root of 2 times a to the 2nd, which is 3a to the 2nd square root of 2. So depending on how your mind works and the way you see these mathematical skills, you could have done it in a different order and still come up with the same answer. So that is simplifying expressions, and as we move on, we're going to talk about, well, there's that word problem, stinking word problem. The door's height is 4 times its width, and then what is the maximum length of a painting that fits through the door? Well, let's see, one moment. Okay, so I have a door, and the height is 4 times its width, and the width is W. And then it wants to know what is the maximum length of a painting that fits through the door. Well, the maximum I can get is something that goes from corner to corner. And I think we could probably use the Pythagorean theorem here. And I know that this triangle is going to look like this. And I'm trying to find this right here. And this is W, and this is 4W. And that would be, remember your Pythagorean theorem is a squared plus b squared equals c squared. So I would have w squared plus 4w squared equals some unknown value. So this is w squared plus 16 plus 16w squared equals some number. So I have 17w squared equals, I don't know, what is that going to equal? But I do know that it's going to be, we'll call it c, right? Because sometimes c squared, c squared, c squared, c squared. And it looks like c could be, find the square root of both sides, and I'm going to get c is equal to w square root of 17. Now we don't know what w is going to be equal to, but we did come up with a formula knowing that this length of c is equal to w square root of 17. So once we found w, we could find out the actual size. Okay, so moving on, simplifying fractions now. We were using the multiplication property, and now we're going to use that division property. That when simplifying a radical, we can rewrite it as the, we have the square root of 144 over 9, and that is the same thing as the square root of 144 over the square root of 9. And then the square root of 144 is 12 over 3, which is going to equal 4. Simplifying that radical. And remember, the radical is going to be a, you can simplify some to help yourself out. That, for example, it's a grouping symbol. So what I could do here is, before I simplify, I could what can I do here? Let's see, I have, I could simplify my numbers real quick. So I could rewrite that as the square root of 36 divided by 4 is going to be 9a over a to the third. So I've simplified my numbers now just to make it a little bit easier on me. And then I have, that can be the square root of 9a over the square root of a to the third. And then we know that the square root of 9a should be, I'm hoping, 3 square root of a over the square root of a to the third should be a times the square root of a. And let's see, remember, this thing right here was the square root of a squared times the square root of a, and we were able to find that and bring it out, just like this one was the square root of 9 times the square root of a, and we were able to find the square root of 9 was 3, and we brought it out. And simplifying here, we came up with this answer, 3 square root of a over a square root of a, and I'm hoping that you see that you can simplify here, that the square root of a divided by the square root of a is going to be 1. So square root of a over the square root of a is going to become 1, so we can rewrite this expression as 3 over a. All right, so moving on. Goodness gracious, here we go again. I have the square root of 25y to the third over z to the second. So I can rewrite that as the square root of 25y to the third over the square root of z squared. And just in case I skipped too many steps in that last one, making some assumptions that you were catching on previously, that numerator can be rewritten as the square root of 25 times the square root of y squared times the square root of y over the square root of z squared. So the square root of 25 is going to give me 5. The square root of y squared is going to give me y, and then I have left behind the square root of y, over the square root of z squared is going to be just z. So there you have it. We are simplified as much as we can right there. Let's see, moving on. Now we're going to talk about rationalized denominators. And rationalizing denominators is one of those things where we're removing the radical from the denominator, because if we can't simplify it, that means it's some form of decimal. And in practice, things that we don't have in the denominator of a fraction, and that's other fractions, it is also decimals, because we're working with whole units. So that's why we have to get that radical out of the denominator. So the easiest way to get a radical out of the denominator is just multiply it times itself, because the square root of, like in this example, the square root of 3 times the square root of 3 is going to give me the square root of 9, which is just 3. So I was able to eliminate it that way. It may not be the simplest form, but it is definitely the simplest way to think about where is that largest perfect square, or the perfect square. And so here we have the square root of 2 over the square root of 3. Well, if I multiply by the square root of 3 over the square root of 3, that is the value of 1. I haven't changed the expression's value, but I do now have the square root of 6 over the square root of 9, and the square root of 6, it's prime, I can't do anything with that, and then over 3. And I've simplified. I have removed the radical from the denominator. So let's see here, looking at this next one, I have the square root of 5 over the square root of 18 times m. And I'm looking to figure out, well, what does it take to make 18 into a perfect square? Well, I can multiply 18 times 2 and I get 36. Well, that's going to be a perfect square. So I can multiply by the square root of 2, and then I have 1m, and in order to make m a perfect square, I need to multiply by the square root of m. So doing that, I have 2m, square root of 2m over the square root of 2m, which is going to give me the square root of 10m over the square root of 36m squared. And the square root of 10m is going to remain the same. I can't simplify that anymore, but I can simplify the square root of 36, and the square root of m squared is going to be, the square root of 36 is going to be 6, and the square root of m squared is going to be m. And that would be simplifying the radical, making sure that I do not rationalize in the denominator, but simplifying it to where I don't have that radical in the denominator. And continuing on to C, hopefully, if you look at this, you know that you can't have that radical in the denominator. So the best way I can go ahead and multiply that by something. And the easiest way for me to get to the perfect square would be to multiply, like we did in our example, the square root of 3. Because the square root of 3 times the square root of 3 is going to give me the square root of 9. And of course, I can't just multiply it by the square root of 3, but I can multiply it by the value of 1. Square root of 3 over square root of 3 is the value of 1. And that is going to give me the square root of 21t. And now I'm able to simplify. I'm able to rationalize that denominator. So in the denominator, the square root of 9 is going to be 3. And in the numerator, I don't think there's a perfect square inside of 21 or t, so I'm just going to rewrite them as the square root of 21t over 3. And that is rationalizing the denominator. And that finishes up radicals, understanding that radicals are working very closely using the same properties as your exponents. So with a little bit of practice, this is going to become second nature. And the big thing about it in higher level math, and even right now, we want to be able to simplify radicals down to a prime number or an irrational number. Most of the math that we're doing does not require a calculator. So just, being able to factor out these numbers, making them simple, really helps us out simplifying these values.